So I'm just wondering, based off what you just said, are you going to, if a question like this were perhaps going to happen, will you make it like last year where it kind of says, hey, here's some steps to go forward, or is it going to be kind of the, okay. I'm just hoping.
Moody brain when you make these decisions.
The newer version was that.
I'm sorry if you've already answered this, but are we going to have the present value formulas?
No.
No, so we'll need to know those.
Yes.
All right.
Well, it'll be whatever is on there. So there's the one pyramid and the infinite string will be on the cover.
Oh, okay.
Okay. The other two are not because in my dream world you would not have to memorize those. You could just do the calculation with these two things, but that's my dream world because I don't really want you to memorize something that you're going to forget on Monday afternoon. And what I'd really prefer you to memorize is, just with these two present value calculation formulas, I can calculate anything by just deploying them the right way. That's my dream world, and so we're going to live in my dream. But if you want to memorize the other two, it's not a bad strategy as long as you remember which one is which.
Can you write those other forms on the board?
Yes.
He's just writing down formulas that are important to Josh or to use.
Not me. Is this something we don't need, or we do?
We do need.
Okay.
Okay, so those are the complete set. This is the fundamental one. This is just an infinite string. This one is built out of these two. This one is built out of these two. Really, that's the way they all go together.
And also, like in the fourth one is also after you pull that f divided r out there, right? So
Yeah,
it
yeah.
also looks like
Yeah.
f r minus
Yeah.
f r over what else have you? They're all not the packet, right?
Yeah. In case it's useful, what you think about these are the fundamental things that I use and that I'd like you to use, and I'd like you to ideally know that those two things are enough to do income calculation. But the kinds of problems that you'll see on the exam often end up like this patent problem, where there's a long period of time that ends, and then an infinite period of time that starts after that. And so having these two things in your pocket ready to go will be handy. Just remember that this is delayed infinite. This is the finite one, because if you flip those around, you get results that are so back up here. Come on. Look, this thing we just went through is a little daunting, but if you practice 2 or 3 of those, you will have practice thinking about social surplus, consumer surplus, present value, expected value. Basically, if you do a couple of those things, you're doing review problems for the entire last part of the course, plus some of the key stuff from the first part of the course. Okay? So just do a few of those things to start with, and you'll find the other ones look, geez, this is simple. It's no time, just an uncertainty problem. No uncertainty, just a time problem. Simple versions of this.
question 4 from the fall 2013 agenda.
Okay. Okay, now this one, if I have gotten the right question, is the one that says continuing the analysis from question 3? Okay.
Yes.
Would it help if I start with question 3?
Yes.
Okay. All right. Yeah. Okay. So this one says, government of large metropolitan areas considering a major upgrade to the communication system used by its emergency responders. The upgrade would cost $20 million per year for 10 years, including 1 through 10. The city would begin receiving benefits in year 11. You can assume that that is gone forever. $20 million would be raised via tax known to cause $0.2 of deadweight loss per dollar of revenue. However, the government is unsure about the benefits. There's an 80% chance that will be $5 million a year, 20% chance it will be $20 million a year. What is the expected impact of that? All right. Okay, so to do this one, the first, there's different places that one could start, but one is by starting on the cost side. So we're gonna pay for the thing to be built for 10 years, and the cost is gonna be $20 million a year, but but since you know the government is gonna have to raise the money with a tax, it creates deadweight loss. You know, the actual social cost of the activity is gonna be more than the $20 million that you pay out directly. So it's gonna be it's going to be $24 million. The $20 million that we actually give to the contractors to build the thing, plus $4 million. So the present value of the cost is $24 million in a finite stream formula. And that's $185 million.
1.05 above that, that's a 20 or a 10?
This
Yeah.
is supposed to be a 10 because they have to spend 10 years building.
Right, that makes sense.
Yeah, sorry, that's just the, okay.
That's all good.
And the benefit side. So the benefits begin in year 11, but they're uncertain, okay? So there's two ways that you could do this problem. One is you could set up a decision tree where you go through, like you were doing on the memo, or like we did earlier, where you draw out a whole decision tree and then each one of them ends in a cash flow diagram. Okay? Where you either get 5 million, you get forever, you get 20 million. Or you could compute the expected benefit and then just plug it into the regular PV formula. So so if I do it that way, I get $8 million as the expected benefit. And then it doesn't start. It goes on forever, but it doesn't start for 10 years. So I have to use the delayed start formula.
Why is it 2 times 20 million? Because it's 0.2.
0.2, yeah. Alright, and so this is 98 million. Minus 87.
What's ENPV?
Expected net present value.
Net.
Yeah.
Okay.
I should have explained that. Okay, so we calculate the expected benefit and we take the present value.
So then the answer to the question is no, the city should not go
Right.
ahead with that.
That's right. Because it's very likely that it's gonna have this payout. Okay. So this is, so that's one way to tackle it. Okay, should I go on, or do you wanna ask any questions or go over any other ways to tackle this one?
Could you go over the way to tackle it? Just
Yeah.
to see?
So. So the other way that might be more familiar is it's gonna look a lot like the decision trees that you've been working on for this memo. Looks like this. So the city has this choice of whether or not to upgrade the system. If it does, then it's either gets high or low benefits. Okay. And then the cash flows. Out here. Are, let's see, that's the high case, which is. So if they go ahead and things work out, then we end up with that set of cash flows, so 10 years of doing the upgrade, at $24 million of cost per year. And then $20 million after that. And if the thing has low payoff, if it doesn't work very well, then you have the same cost, but they get the smaller benefit stream, and you could just calculate the NPV of each of those branches, and then take the expected NPV of this node. And you find that it's exactly the same as what we just calculated. Okay, so doing nothing is better.
Go over that piece one more time.
So after you calculate these two PVs,
Yeah.
NPVs, and then to simplify the tree, you have to go back here, and since this is a chance node, you have to take its expected value. Because that's 0.2 times the payoff of this plus 0.8 times the payoff of this. When you calculate it out, you'll find that it's exactly the same answer that we had a few minutes ago. So the upgrade has a payoff of minus 87 million. Doing nothing has a payoff of 0. Doing nothing is bad.
Can you walk through that?
I mean, can I, maybe, let's see. So this is the present value of the benefits that will arrive from here. Minus the cost that you pay in 10 years. Okay. And then this is the payoff of the second branch. Okay. And you calculate those out and you take their expected value. And this thing, I think, turns out to be minus 124. And this turns out to be 60. And that gives you minus 87. So either way, it's totally total. So on this particular year, the most frequently made mistake, other than messing with present values, was people decided that they weren't sure what to do with the deadweight loss of 20 cents per dollar of revenue, so just left it out. And counted the cost as being essentially 20% less than it actually is. So try not to do that.
So with the deadweight loss, could you also just like calculate out, like 20M over 0.05, do like the finite stream, and then just take that number and multiply by 0.2?
You absolutely
Okay.
can, right? So you could calculate out this thing with 20 in there and then multiply it by 1.2. That's, which I think is what you're saying.
Mhm.
Because the 1.2, this thing here is just 20 times 1.2. So it's perfectly fine to factor it out and multiply it that way.
Okay, excellent.
Basically, the idea, that's actually the D point, right? The point is that the total social cost is going to be 20% higher, whether it's the outflow or the present value, in either case, 20% higher. Okay, now, the actual question was, who would do question 4, right? So let's do question 4. Any other questions about this? proposes the government could hire a consulting firm to determine whether the benefits from the upgrade would be high or low before it commits to the project. It would pay the consultant in year zero and receive the results of the study 3 years later. Okay. It could then decide whether or not to go ahead with the upgrade in question 3. To be specific about the timing, the government would receive the report and decide on the project in year 3 and construction would be in year 4. Okay. What is the maximum amount the government would be willing to pay for the study? Okay. Okay, so just going through the analysis, if the government decides not to do the study, then what's its payout? Zero, because it chooses not to do the project. Okay. Now, that's not always the case, right? It might turn out that if the project would still go ahead, that might be improved by some information. But in this case, what we worked out a minute ago, the wouldn't do the project. Okay. Okay, if they commission the study, then we reach this chance mode where there's the same possible outcomes that we had before, high or low. Okay, and then after the study comes back, the government has to decide whether or not to go ahead with the upgrade. Okay. And so in this case, if the study comes back and says it's only going to be $5 million a year, okay, in benefits, what would be the right decision? Based on what we did a minute ago. If you knew with certainty that you're only going to get $5 million,
No, you wouldn't upgrade.
yeah, you wouldn't upgrade. So if you could see that as an outcome of the earlier analysis, you didn't have to redo the analysis here. You just say, if we go ahead with the study and the study says low, then the only payoff, then we wouldn't want to do the upgrade without going through all the calculations. But we do have to pay for the study, okay? Because it was not conditional on outcome.
Oh, okay.
So you have to pay, so the question says what's the maximum government's willing to pay for this study, so we use X for that. So they commission the study, and it says payoff will be low, you wouldn't do the project, and the payoff for the city would be X. All right, so okay, so if the government orders the survey, it has to pay X, and if it chooses to go ahead with the upgrade, it has to pay for this upgrade cost, $24 million a year for 10 years, and then it gets the $20 million payoff. And it turns out if you remember what we did just a second ago, what happens if the government goes ahead and does the upgrade, it gets the $20 million payoff, it's like getting the good outcome from the first case, but 3 years later. Okay, so the second way we did the second way we did the analysis, we calculated that the NPV of the good outcome was $60 million. Okay, and so you could calculate this out by hand, or you could just observe that it's exactly the same cash flows we have in the second piece of the last analysis, delayed by 3 years, and just plug in the 60 million over 1 plus R cubed to get the payoff for that outcome. So what you find, if you do that, is that doing the upgrade produces a payoff of 52 million minus X. Not doing the upgrade is minus X. So if you arrive at this note, doing the upgrade is clearly better.
Can you just run through again that last part?
This thing? Okay.
Once you get to like the 69.
So,
Year 3.
let me just try to clarify, because I don't think I explained it very well. So a minute ago we had, this is the cash flow from undertaking this upgrade and having it work. Okay? And what we calculated was that the net present value of that was $60 million. Okay? And what I was going through here, in case it wasn't obvious, is I was just looking at the cash flow. You still have to pay 10 years to build the thing. You still get an infinite stream of payments after. What's happened is you get exactly this cash flow, but it starts 3 years later. Instead of starting with the first payment in year 1, the first payment arrives in year 4, right? It's delayed by 3 years. So if you just think of this as being the payoff once you start construction, okay, then we can quickly calculate the net present value of starting construction but delayed by 2 years by just taking the 60 million we got out of there and dividing it by 1 plus R2. And you didn't need to do the problem that way. It was like perfectly fine to calculate out the finite stream and the infinite stream delay. But this is a little sort of sales pitch that if you look at these problems and you kind of look at the cash flows and see how they line up, you might be able to cut huge chunks of calculated time out of doing the exam. Okay. To be clear, people this year had plenty of time to do this. They didn't need to see this. Okay. But some people did see it and they basically could do this part of the problem very quickly. Okay. So working backwards, what we've shown is that if the consultant says it's low payoff, you pay them and you don't do the project. If they say high, you go ahead with it and say that ED is 20% chance of a really good payoff and an 80% chance of just having to pay the consultant. Then the EV of that turns out to be $10.4 million. You can probably see that right out of 22 times this minus X. So as long as the study costs less than what, you get to do it.
10.4 million.
Yeah, $10.4 million. Okay. And the value of the study is that it allows you to avoid doing the upgrade when the upgrade is in the middle. Okay, so if you might have gone beyond this point, but if you're wondering, does this ever happen? Yeah, lots of cities have this problem when they're trying, after in the post 9/11 world, trying to figure out how to coordinate the communication systems and other emergency responders use. If everyone was coordinated, it would seamlessly, there's huge payoff, but it's hard to integrate all these systems. What do you want to do next? Please, Mike, you answer. Maybe you guys aren't playing Hannah, but, so it's a possible answer.
I'm afraid if we ask one more question, we'll stay for another hour, you know?
And you're not obligated to say your answer.
No, I would. No, it's pretty.
Let's watch it later.
See you all Monday, good luck.
Never mind. $4 this one. One's the spring, she said it was
Can I ask a satellite question for Leslie? Okay, one moment, let me pull this up.